Alright, for this portion of the notes, we're going to talk about types of experiments that can be run. And we're going to learn formally about 3 specific types of experiments. One type is a completely randomized design, which is the one I was explaining before, actually. Next is going to be a blocked design, and then a special case of a blocked design, specifically called a matched pairs design. We're going to learn about the 3 and then actually see examples as to how to design an experiment. So types of experimental designs. First type, so introduced, is a completely randomized design. In a completely randomized design, all subjects are randomly assigned to the treatment groups, whether they be 2, 3, or more. In my example of the headache pill, I had 3 treatment groups. They were randomly assigned. Everybody was randomly assigned to one of the 3 groups. Fake pill, 10 milligrams, and 20 milligrams. So here's the general idea, though, and I'm trying to use vocabulary that we've learned in explaining it. So experimental units are split into the treatment groups through random allocation or random assignment, or one word, randomization is what that entails. All units in one group then receive one treatment, and all units in the other group get the other treatment, or a placebo for a comparison. That's a specific example when there's only 2 groups, but there could be more. Responses in the one group are then compared with responses in the other to see if the results are statistically significant. So that's the general approach. Let's take a look at, again, pause as necessary. Let's take a look at a specific example. Oh, sorry, I'm going to get to examples next. Let's take a look at the next type of design, excuse me. So next is a blocked design. In a block design, subjects are first split into groups called blocks. Subjects within each block have some similar features, the important thing. For example, gender, age, education, ethnicity, etc., that can create variability in the responses. Then within each block, subjects are randomly assigned to the treatment groups. Bold part's important, which is why it's bold. The goal of blocking is to reduce variability. That's the point of it. It's really a form of control. It's a form of control. When blocking, we try to create blocks as homogeneous, similar, as possible. Different blocks should be different in ways that may affect the response variable. Each block then acts as its own mini experiment. So for this one, let me go to my headache pill and say, what if I wanted to use blocks? Why might I want to do that? What if there's something that I already know in my form of control that I can't control for, but it's a difference that I recognize? I'll use gender as an example because it may be the case. I believe that women and men, males and females, tend to experience headaches and a lot of drugs differently. And maybe I think that might be a case. And the thing is, if I just have men and women together into different groups, I might see variability in how much effect the drug has on curing the headache. And I won't know, again, this is the issue, I won't know if it's the actual headache pill and the amounts of the headache pill, or if it's the fact I have males and females. So what I try to do then to account for that is I say, let's have one separate experimental group for females and one for the males. That's block. So I'd have 2 blocks, a male block and a female block. It's done right in the beginning. It's no random assignment, obviously. We just would have a separate experiment done for the one and a separate on the other. So then all the males would be separated randomly into the 3 groups, placebo, 10 milligrams, 20 milligrams, and then in the end, after a while, compare headache reduction. In the females, separate experiment, really. You see the females separately, randomly assigned into the 3 groups of placebo, 10 milligrams, 20 milligrams, and after a set amount of time, compare headache reductions. In the end, notice there's no goal in comparing the 2 blocks to each other. We're really trying to see how much reduction, if any, does the headache pill cause. And I don't want the variability in males and females in there. I just want to see headache and headache. I just want to see headache pill and headache pill, I should say. So here's an example with males and females that you have there. It's on your sheet, but men and women are subjects to the experiment where responses often vary with gender. It's not always males and females that's blocked. It's anything we think is going to create a difference. Men and women are split into 2 blocks. In the male block, the subjects are randomized into 2 groups, with half receiving the treatment and the other half receiving the placebo. These 2 groups' responses are then compared. Women in the female block are then also split randomly into 2 groups, treatment and control. These 2 groups' responses are compared. And in my example, I actually had 3 treatment groups, but it doesn't matter. It's as many treatment groups as you have based on levels and whatnot. So here's the third kind. This is a matched pairs design. Before I move on, I should say that this is the actually most impressive experiment we can run. This is the one where when applicable, when we can do it, we can reduce variability better than anything. So you can really just find out, is it the headache pill or not. Before I move on, make it a goal of yours when designing an experiment to see if you can do it in a matched pairs form. There's nothing like comparing apples to apples when you're trying to find out if there's something different between apples rather than apples versus something else, apples and oranges. Let me show you what I mean. So in a matched pairs design, first off, there can only be 2 treatments, so I'd have to change my headache scenario a little bit. But in each block, there's here's one way you can do a matched experiment. There's a single subject, in this case a person. It could be an experimental unit, but it's a person. And that person is going to receive both treatments. Let's see how that might look, all right? So maybe I could do that. It's tough with drugs because they have long interactive effects and things like that, but let's say maybe I could do that. What I would want to do is have one subject get both treatments. Say they'd have the headache pill, 10 milligrams, and placebo, all right? What I could do then is sometimes when they have the headache pill, I'd randomly decide, it has to be random assignment, randomly decide if they're going to get the placebo, and other times when they have the headache, I'd randomly decide to give them the actual true pill. They wouldn't know which one it is, they're blinded and everything like that. But at the end, imagine how great that'd be, because I'd really be able to compare headache reductions. And I'd say, well, did their headache actually get better, faster, or more so in the set amount of time, I guess, when they actually had the drug versus not. Imagine how great it would be to compare somebody to themselves and all those other variables. That's why it's so powerful. That's the one kind. The other kind of matched pairs design is like this. We have a homogeneous pair of subjects. Think twins. We often call these twin studies. Sometimes when we literally have twins, people who are twins, or just when you have 2 things that are very much alike and they can act as twins, similar. And in this case, each receiving a different treatment. So imagine if I actually had twins, how that might look. What if in my classroom I had only twins, all right? Or my volunteers were all just twins. What I would do is, for each set of twins, I would randomly decide, which one's going to get the actual pill and which one's going to get the placebo. Do that in all the sets of twins. After a set amount of time, I'd measure the difference in headaches, but I'd just get a difference in headache here for sets of twins. So again, imagine how powerful that is. Nobody's more like another person in themselves, and a twin is the next best thing. Right? Genetically, they should be the same, especially if they're identical. Fraternal would still be very helpful. We would still do that. They don't have to be exact twins. For instance, even speaking of twins, fraternal twins would be the next best bet, right? But things that are similar, could be similar in age, something that has to do with that. So again, when applicable, try to design a matched pairs design. You try to use that format. Here's the matched pairs twins. The drug is being tested that can be confounded with genetic differences. Each pair is 2 subjects in the same family, right? So they're not really twins, but at least they're siblings maybe. Each pair, it's randomly decided which person will receive the drug and which will receive the sugar pill placebo. In each pair, the difference in responses of the 2 is recorded. The average of all the differences is recorded and noted. So what is the overall difference then? So next I'd like to walk through an example of each kind. So let's take a look at the completely randomized design of an example. Making a real simple, quick case. A food company assesses the nutritional quality of a new instant breakfast by feeding it to 36 volunteers. Let's say the response variable is a volunteer's weight gain over a 28-day period. Maybe that's the goal. Design the experiment. When you design an experiment, you should be clear about it, write in sentences. What I like to do also, though, is sometimes write a little diagram for myself as I go. This is a diagram. I'll realize when you're making a diagram, you still must use complete sentences, complete thoughts, because nobody's going to guess what you mean by your arrows, but it can help organize your thoughts, and even the structure can help organize somebody else's thoughts in reading it. So that's what you're going to see here. This is a completely randomized design, that first case. So we randomly assign the 36 volunteers we have, said 36, so that, and that's the important part, gotta do that. It's not an experiment if you don't randomly assign or randomize. I'll split in half, right? 18 will get the new instant breakfast, and 18 will get the old instant breakfast. Realize I don't need a control group getting nothing or a fake food. This is my control group in a way, right? They're getting the old breakfast. I want to see if the new one's better. In the end, responses. Compare the average weight gains of each group. See which one gained more on average. Realize that a design would have to have, first off, random assignment, explaining the treatment groups, what they're going to get, and in the end, how we're going to measure effect, what the response is going to be. Notice this is a diagram, but it's still actually a couple complete sentences as it goes, so it's good, it can be followed. So, next case. Let's look at a randomized block design. We often just call this a block design or block design, but there is randomization in it. Researchers want to test the effect of a new estrogen supplement on menopausal women. But they have reason to believe that women who have had hysterectomies will react differently to the treatment than those who have not had the surgery. Design an experiment to test the effect of the new estrogen supplement. So notice the problem itself doesn't tell us to do blocks, but we've been given the information to know that we should make blocks. We already know there's something we'd like to control for that you can't control for. I can't say, hey, guess what? You don't have a hysterectomy. Or guess what you do? All of you do. They either do or they don't. So I'm going to separate them before it starts. We're going to have a group who have had hysterectomies and a group who haven't, and run mini experiments. Remember the purpose of this, it's control. I only want to find out in the end if it's the estrogen supplement that's having the desired effect. Not, I don't want to see and I don't want to have in there confusion about is the hysterectomies causing an effect or not too. So I'm going to use the diagram in this also. You never have to use a diagram at all, but sometimes it can help. It's a little messier with the block design, so there's an added step. So blocking comes first. Menopausal women are blocked into ones who've had hysterectomies and the ones who have not. So notice we're going to do a mini experiment on this group and a mini experiment on this group, and we're not going to compare in the end. That's not the goal. So now we randomly allocate half the women from each block to the new estrogen pill and the old estrogen pill. If it's harder to see that, I would have to say randomize into pill, fake pill, pill, fake pill. Oh, sorry, new pill, old pill, new pill, old pill. Notice the importance here, this is where we randomly allocate, where we randomize or randomly assign. You gotta do that or it's not considered an experiment so we can show cause and effect. And we'd compare estrogen supplement effects in the hysterectomy group. We'd separately compare estrogen supplement effects in the non-hysterectomy group. Notice it's not a goal to compare which was better or not. We'd probably do that, but that's not the goal of the experiment. The goal of the experiment is to see the effect of the estrogen pill. And now I'll have an idea, and I won't have to worry, really, if hysterectomies had an effect or not. I also often won't have any idea if it did or not, because the idea just reduces the variability within the groups. I won't even know if there was any a lot of times. So don't make that the goal, because often you can't achieve that anyway. Let's take a look at the matched pairs design. So, example of a matched pairs design, I'm going to do the blocking with 2 in each block, right? That's always the goal. Now sometimes it's somebody getting both treatments, or it's 2 kind of twins getting both treatments. You're going to notice this is kind of both in a way. You know, let's say, is somebody's right hand generally stronger than the left hand in right-handed people? Right. Now notice this is a neat example because, you know, I wouldn't compare my right hand to other people's left hands. We're different people, we have different strengths. But what a great way to compare my right hand to my left hand in terms of strength, right? That's an element of control, and this is going to be matched pairs. It's sort of the idea where one person is getting both treatments, but it's also more so, it's kind of the idea of having twins in a way. Right? So you can crudely measure hand strength by placing a bathroom scale on a shelf, think about that, with the end protruding, and then you squeeze the scale between the thumb below and the 4 fingers above it. The reading of the scale shows the force exerted, so we could even do this in class. Describe the design of the experiment to compare the strength of the right hand and left hands using, say we have 20 right-handed people as subjects, right? Just to keep things simple about hands, all right-handed people, right? So let's take a look at how this would be. Now, for these, I tend never to write these out in diagrams. I go full sentences. I'll explain that in a second. So I'd randomly allocate, gotta have that, each person to either get the right hand first or the left hand first. Squeeze subject squeeze once for each hand, calculate the differences for each person. Next, we'll calculate the mean of the right minus the left differences and see what it looks like if it's positive, negative, and see if it's statistically significant if it is positive. Now, a couple things. Notice you can kind of forget sometimes that you need to have random assignment of the treatments, right? So the treatments are actually squeezing that scale. It's a kind of dubious sounding treatment, right? Treatment just means the thing we're going to have people do, really. So we can still do that. Think about why that might be important, though. Sometimes you're not aware why it's important, but in this case, there is a reason. There's something called a learning curve, where people tend to get better at something as they do it. And it happens with everything. Squeezing a scale would be no different. You might figure out in squeezing the first time, I should have put my thumb there, I could get more force or something like that. It's silly to think about this way, but sometimes you get tired after the first time. You're doing something, you got to do it next. Or just the fact it's later on in the day, maybe you're more hungrier, you have to go to the bathroom, things like that. There are all kinds of things we don't know about. So what's important is notice what we'll end up having is basically half the volunteers in this case will be using the right hand first and half of them having use the left hand first. And then they'll switch and they'll use their left hand and the right hand the second time. So remember that idea of control. The idea of randomly allocating. It evens out all that learning curve or getting tired stuff, so we don't care. Don't forget that. But anyway, randomization, we're explaining what the treatments are, and we're explaining what the responses are, and that's what it looks like. You can notice that why I wouldn't choose to use a diagram. If I chose to use a diagram for this case, I would have, well, how many people? 20 people. I'd have 20 little brackets coming out in comparisons, which I could do and write it in sentence form, but I find it easier just to write the whole thing in sentence form that way. But it's always your choice. Just design them, make sure you have clearly what you're doing with the volunteers in terms of random assignment, what the treatments are, and what the responses are you're going to be measuring in the end, and you can be really light about the idea of randomly allocating. Watch out for when questions ask you to explain your randomization method. Or I would ask you to. That's where you would off to the side say, to randomize, I would say, oh, put all the volunteers' names into a hat and shuffle it up and pull the names out one by one. First person gets treatment 1, second person gets treatment 2, etc., etc. Or easier, number all the volunteers, in this case 1 to 20. Let a random number generator randomly order those numbers. The first 10 people then would get the right hand, the second 10 people would get the left hand. That's ways to do that. That's how we can explain the randomization method or describe that. That's all I have for